Okay. So we're on chapter 16 now. This one's going to be the infrared spectroscopy and ultraviolet visible spectroscopy. Who here has used the visible light spectroscopy? Who's used infrared? UV? Nobody on any of them?
I don't know.
Okay, so technically you've all used visible light spectroscopy. Your phones do it automatically for you. It's how they figure out what lighting conditions they want to use. But, Okay, so this is going to be the sort of intro to absorption spectroscopy is a good way of calling this. It's going to be electromagnetic radiation that is absorbed depending on the properties of your compound, right? And so the electromagnetic radiation, this is going to have characteristics of both waves and particles. This is an important formula you're going to need. This actually shows up in general chemistry, in case you're wondering. So that's where you should have started learning about this. You may have learned Beer's law. Okay. So this right here is C. C is what? Speed of light. This one is wavelength. Yep. And that is lambda. Okay. And this thing that looks like a V is not actually a V. That is frequency. Okay, it's another Greek letter. So, but everybody always italicizes V and just uses that. because. Learned that in physics?
Just last week.
Did you? Good. Okay, so this right here is going to be a wavelength. Wavelength is measuring from a peak to peak or trough to trough. It actually doesn't matter. Okay? And so this right here would be peak to peak. That would be your wavelength. You could also measure trough to trough, same number. Okay, so what we notice is that frequency is going to be the number of times that peaks would pass a given point in a given amount of time. Okay? Frequencies are normally measured in hertz. Everybody's seen HZ or HERTZ? Okay. Does anybody know what that unit actually is?
Number of cycles.
Number of cycles in what time? Yeah, it's in a second. So a hertz is actually 1 over seconds. It's the number of cycles in a second. Okay? So that number is just the number of times a peak passes a given point in a second. Okay. Now, notice that's the exact same sort of thing that your car engine tells you, RPM, right? Assuming you have a non-electric. So RPM, rotations per minute, number of times it passes in a minute, right? Okay. Okay, so the wavelength and frequency, these are going to be inversely related. As your wavelength gets longer, then your frequency is going to get smaller, right? Longer wavelengths means less times you pass a given point in a second. Does anybody know how this relates to energy?
E equals more wavelengths, more energy.
So, okay. So, the energy of a photon, or the energy of light, given one single particle of light, if you will, which is referred to as a photon, is going to be Planck's constant times the frequency of that photon, or the frequency of that light. Okay? Another way of putting this would be we can substitute this formula into this formula, and we get this right here, which is Planck's constant times the speed of light over the wavelength. So the longer the wavelength, the lower the energy. The shorter the wavelength, the higher the energy. Anybody ever heard of like short wavelength UV radiation? Or high frequency UV radiation? Nobody's ever heard of that before?
I've heard of UV light.
Okay, so UV light is shorter wavelength, higher frequency than visible light. And the reason that this might have been something you'd heard of is we almost wiped out all of humanity. Do you guys know that?
The ozone?
Yes. Yes. So we put in chemicals that broke down once they got above the ozone because of high frequency UV light, or low wavelength UV light, or high energy UV light. Remember all those times that I was always like HV and that start of reaction? That was high frequency light, right? High energy light. Okay? And so they broke down the CFCs is what those were usually called. Those are several things that also do that as well. And these chlorides then acted as a catalyst in the ozone layer and did a chain reaction where they destroyed many, many, many ozone molecules. Anybody know what the ozone layer actually is? Ozone is O3, yeah. So the ozone layer is actually where the ozone density settles out in the atmosphere. So you know how you put like a bunch of different solutions that have different densities? And the middle density would separate out in the middle, right? Same thing happens to the ozone. That ozone is actually created in the upper atmosphere by very high energy UV light, the highest energy type, which actually creates the ozone. The ozone then is more dense than O2. It settles out lower in the atmosphere, and then it captures the next highest frequency of UV light. And so down here on Earth, we actually end up with the lowest energy UV light, and that's mostly what we get for UV radiation. The high energy stuff, does anybody know what it's used for in hospitals? You can use it for cancer therapy. Basically, you just kill any living organism that you expose to it. So, for example, you can use it to sterilize equipment. That's it. Oftentimes, it's used for that. You can use it to sterilize water. You can use it to kill off cancer. High energy UV light is within about 10 minutes to 15 minutes kills off any living organism you can want to kill. Okay? Or don't want to kill. So if we had actually destroyed the ozone layer, the entire surface of the planet would have had all life annihilated off of it. The only thing that would have survived is in caves and like 3 feet under the ocean. Okay. Yep. Yep.
I feel like we could have done that.
Yeah. Yeah. Anybody ever seen Futurama?
Yeah. We just dropped the
Atlanta. We could have been like the Atlantans. Okay. I guess my time is almost up. Next, we're going to talk about electromagnetic spectrum. And keep in mind that, again, the energy of a given photon, the energy of light, is directly proportional to frequency. It's directly inverse to wavelength.